I'm Daniel. I'm from Linux Technology Center also. So what I'm actually talking about is a result of when Phoronix back in June did a benchmark on the Talis 2 workstation on the Power 9 chips. And while a lot of the benchmark results came across quite well, we looked at some of the tests and go, we shouldn't actually be that bad on it. So what we found as we looked through some of the poorer performing tests, there were a number of factors, namely, the application wasn't well tuned for the test, and with a little bit of basic performance, use of basic perf and compile time and build time options, we were able to improve the performance. So that's what I'm going to cover today. So I'm going to start really basic, i.e. this is a CPU workload that isn't doing any CPU. If you have this, don't try to improve the performance on it. Wait till you've got something more like this, which is all the threads actually in use. And so once we've got that, whether it's across all threads or it's a single thread maxed out, we've got some actually opportunity to know that it's going fast as possible, and we can improve the performance on that. Occasionally we'll get a result like this, which was the Blender test in the Phoronix test suite for this. And this was apparently a CPU test, but down on the very fine print is the word like GPU right here, which was the first indicator that maybe that's some reason why it's only running 16 threads. Now, after searching the code base for things like max CPUs and all, another few dead ends that way, discussed someone who actually knew something about Blender and how to use it, and discovered there's a thing called tile size and 256 by 240. A tile size, when you're producing a 1K by 1K image, doesn't leave actually that many threads that can be used. So what typically happens with CPU workloads, so I found out, is this figure is more like 32 by 32. So, and that's why the Phoronix test suite had a Blender file, a GPU and a CPU version. It's just they weren't using the CPU. So that was easy to fix. So for harder problems, we start by using perf to identify where in the application stack is the problem. So the first thing when you're actually using perf, it's good to actually resolve addresses to actual symbols and function names that actually are a lot more meaningful. So every distribution will have a bunch of debug info that can be installed in various ways. Or if you're compiling your own, you just use the -G C flags or C++ flags to get debug symbols on those. So using the perf top command, this is what the Blender workload was running. And as we can see, if we were interested in improving the performance of this, the top two functions of that are consuming like 37 and 23%. And those would be a good place to start. And this is just like C++ names, so it demangles quite easily after that. So for something a bit longer run, we want to actually do a perf recording. So we use a perf record -G to get the full stack. We specify an output file name. We specify the process ID. I've just gone pid on Python, and so this is for the scikit-learn application. And I've just done sleep 30 at the end, and that's just telling the perf to record for 30 seconds. So when I do a perf report based on the same input file, adding a little percent limit so it doesn't go on indefinitely, we see this is like a top-down view of the stack. So up the top, we see the second line, most of it's in like the main function. Go down a couple more lines, it's all under Python main. And we go down and we really can't actually see an obvious place to actually apply performance improvement. So the key with actually using perf report is to use the no children option. So when we use the no children option here, we can see most of the CPU time in this benchmark is in an underlying library called BLAS in this one function called DGEMM, which is just a mouthful, especially when you've got a cold. So the no children helps to identify which functions need to be improved, and in this case it's not actually in the Python library or the scikit test, it's actually in an underlying library. So the underlying library was pulled in by NumPy, which is a Python numeric library, and we see with the distro tools that in this case of Ubuntu that it depends on either libblas or anything that provides the libblas.so.3 library. Using an app file search, we see there's another implementation called OpenPOWER, which has received some optimizations. So by simply just doing an app install libopenblast base, it will actually replace the existing implementations with the optimized one, and it's ABI compatible, so it'll and rerunning the test, we go from the test running at 328 seconds down to 26 seconds, which is a pretty good performance improvement for just installing a different package. See, I told you this was all basic stuff, once you know how. If we look at like the perf report of it running under OpenBlast, we see that instead of like the DGEMM function there, it's been replaced with a couple of similar looking names, which are obviously the power optimized versions of those. Another test was like the OpenSSL in the Phoronix, and the version tested was version 1.1.0, and when we just like pulled down a latest version of 1.1.2, we discovered some work had actually gone on, and we were getting an RSA signing speed of twice the rate and verifying about the same. So just trying a later version can often give you a performance increase. The third test, third, fourth, what number am I up to? One of the other tests that Phoronix did was on an MP3 benchmark using the lame MP3 encoder. So in the perf profile report, this is showing that like the count bits is at the top of the usage. So this isn't a kind of function name that sort of implies it's going to use a lot of CPU. So we looked a bit closer. We installed using Phoronix and looked at the install log and found that it was actually compiled with like no optimization flags at all. So to give you a quick demo on, what different optimization flags we can do, I've compiled the lame with -save temps, so we get all the pre-processed headers are actually included into one file, which makes it easier to copy into the compiler explorer. So what I've done here, this is basically cut and paste from the output of that file so we've got this count bits function, and what I've needed to do is just grab a number of other things from that file. So while there are some power compilers up here, I'll just do the easy option and do target equals power PC 64LE, and this is like just in real time. Well, it's sending the file to the server and getting it to compile. And it's a quick way of testing what changes are going to happen. So to test this a bit more, and geez, that's ugly. Damn. Here's one I prepared earlier. So what we got is like one window here is where we've got one compile option. Over here we've got the other, and we've got a difference view down the bottom. So as you probably saw partly there, one thing you can do to improve the optimization when you can type correctly is do like -01, and what this shows is that the output is actually different. And if we look down the right hand side, we can see that the output is like significantly smaller. It's used a lot of larger addresses on things, and that's especially in like the main body of the loop, and it's used some distinct instructions there. So that's just at the 01. If we want to go a little bit further, let's change the base to 01 and see what difference 02 makes. So unlike 01 before, where we got a significantly shorter one, what we get with 02 is the actual code is significantly longer. And see up the top, so in the beginning of the functions it's staving off all the variables to the stack. So a hint that it's saving off more variables is it's actually using more variables. And we can see that further down, that we've got, instead of a little loop here, we've got a bunch of vectorized operations down here. And despite being a longer function in this case, it actually Power pipelines these kind of instructions quite well. So this is one way of achieving a performance increase. If we have a look at 02 and seeing what difference 03 makes, we find it makes no difference at all. 02 and 03 are actually the same output for this particular function in the entire data set. So, question C, if you're still awake, what other optimization could we actually try on this compiler? Yep. Yep. So if we say 02 as a base, okay. So the option was -m tune. Actually, I'm going to use mCPU equals. So let's just start with like power 8 to start at a baseline, and it's made no difference. It's actually treating power 8 as the basic change for this anyway. But if we change it to power 9, we see that the output code is being reduced again. And so whereas before in power 8 we had these instructions, I don't expect you to know assembly because I don't know them that well either. We've got a bunch of operations here, but once we've told us the compiler that we're going for power 9, we've gone to the vectorized operations that are supported on power 9. So it's no surprise from there that we tried those 03, 02, much the same, and mCPU is like power 9, and reran the test. So we removed the existing one and reran it. And what we ended up with is going from 98 seconds down to 21 seconds just by adding compiler flags. Joel, who did the test, also looked through the code, and there was a feature called fast log that wasn't enabled by default on Power. Presumably just someone hadn't tested it. Worked fine, generated output, and shaved another couple of seconds off the benchmark. So I told you before that the Phoronix way of running benchmarks in the Open Benchmark test suite has got a bunch of build logs. Distros actually include build logs too. they're just a little bit harder to find. So I'll put these up, and a bunch of ones are there. You can find them eventually through the Launchpad packages. Fedora ones are a little bit easier to find on Koji to there. And we see that Lame, at least in the distros, has got like a -02 flag. They've got to support Power 8, so you know it's tuned for Power 8. One other function that wasn't actually part of the Phoronix test suite, but was something I was testing for a customer, was just an OLTP test on MariaDB. So this is MariaDB 10.3.9 on just a basic database test. And we see that like there's a memcopy function right at the top using 4.8% effectively of the CPU. So what happened in GCC 2.7 was there was a bunch of tunables added. One of the tunables was an optimization where you could tell the GCC library within a program that it was operating on cached memory. So why this is important for memcopy was there's a bunch of instructions that can actually copy quite quickly, but they don't actually work if you're on like memory mapped I/O. So those couldn't actually be enabled by default. However, knowing what MariaDB does, it doesn't actually operate on memory mapped I/O devices, so it can tune this in the environment. In this case, I put it in a systemd service edition, and what we see is that the previous 4.8% of in the memcopy has gone down to number 3 on the list, which is 3.3% of CPUs, and used a different function in the process, one especially marked for cached memory. This is in glibc, so it doesn't matter actually what you compile with it, as long as it's GCC, what did I say, 2.27 or above. glibc. Did I swap them again? Definitely glibc. Yeah. So yeah, and that's what's in the latest Ubuntu LTS release, and undoubtedly Fedora, and yeah, those are probably the main two more bleeding edge ones on Power. So the other thing can do with perf output is there's this tool that Netflix guy called Brendan Grigg wrote, who does like flame graphs, wrote this flame scope. And so what I've done here is I've loaded up the perf recording that I did before, and this is a representation of time actually going through. So we can see here that the workload of the MySQL test suite where I recorded was fairly uniform by the color. There was a glitch early on. I suspect that was not related to actually what it was running, but it was just the process of initializing the test suite, the perf recording. So I can select like an interval here, and this will display a top-down view of what's happening. So it's a MySQL process. So unlike before when I was recording just a process, here I've recorded everything on the system, which you can tell because I've got the test program running on the same system, which is just sysbench. And so this is, a bottom-down view of what's actually in the stack. So where this might be useful is if, say, there was a background process in another area of the stack, you could actually compare the two outputs and see, make sure that what you're seeing in your perf report results maps to something you actually want to optimize, rather than maybe a background process which may not be as important. Okay, so it's a time series graph. So this is just, where the mouse is the beginning of the samples, and it just goes on, and it's done for some reason 30. Oh, that's right, 30 seconds down the bottom in the fine print, which isn't very obvious, and to be honest, I'd never noticed before. But yeah, it's the perf does by default sampling at some sample rate. It's just a rolling down axis. So we got 1 second and so many milliseconds going down. Yep. No worries. And so that's it. So in short, I haven't changed a single line of code here by using recent releases, ABI compatible functions, equivalent libraries, optimization flags of like -02 and the MCPU to the right version. Enabled sometimes experimental features or features that haven't been tested much on Power, but are usually fine, and used GCC tunables. We've actually got better perf results, and I've showed you a couple of perf tools and that can assist with the diagnosis. And as Jeremy said earlier, there's a Stack Overflow group if you trying to optimize a Power workload and have a narrowly scoped question that people may be able to answer. There's a PPU's emails list for those grey-bearded ones. And so there's a bounty source program where IBM has offered people in the community money to actually fix some of these problems in open source projects. However, if one is particularly affecting your company, maybe you can either add your own problem or up the bounty for something that's already there. If you come across like some -0 flags somehow missing from distros, you can file a distro bug report and get it fixed that way, especially if you can show there's like a performance benefit in some way. And the compiler explorer is pretty good. Up there, I've been meaning to, I've half written some code to improve the version numbers on some GCC compilers up there for Power, because they don't cross-compile as easy as the CLang ones by certifying target. They've got to be their own entity. And that's all I've got time for, so is there any questions? How am I for time?